Welcome. In this lecture, we are going to talk about functionality in mixed signal oscilloscope for validating digital control. And here I am Dr. Shantanu Kapat with Nitin Nigam from Keysight Technology. In this lecture, we are going to talk about characterizing digital control using mixed signal oscilloscope and then need for dedicated analog and digital channels. And in this particular lecture, we will be taking this text kit, hardware prototype of a digitally controlled buck converter, and using Keysight mixed signal oscilloscope, Nitin will present the hardware demonstration using mixed signal oscilloscope. I will hand over to Nitin.
Hello. In this lecture, we learned the need of the mixed signal oscilloscope and the use of the digital channel in the testing and the validation of the buck converters. In this section, we have taken a Keysight MXR series oscilloscope which has 16 digital channels inbuilt into it, which can be used along with the 4 or 8 analog channels simultaneously. We have connected the digital channels on the gate pulses of the signal. As you can see from the oscilloscope, we have two specific pulses, the gate pulses, which is one gate high and gate low. We have configured the channel in the digital specifications of the menu. When we go into the setup, we have a specific digital channel menu where we can switch on the specific channels which have been connected on the oscilloscope. Since we have connected two specific gate pulses, so I have switched on channel number 6 and channel number 5, and I have annotated them as a gate pulse high, which is Q under H, and the gate pulse low, which has been connected. We have connected the channel 2 as a current, which is the inductor current also being connected. As it can be seen, there are various functionalities that adds to the extended capabilities of the oscilloscope. Digital oscilloscope does not only not have the analog capabilities, they also have the mixed channel capabilities. That means you can analyze the analog channels and the digital channels simultaneously, which are a very useful concept when it comes to debugging of such type of converters. Along with the voltage and the current signals, you can also analyze the gate pulses, what exactly we are doing in the system right now. There are a couple of triggers that can be done on the specific channels. From the trigger menu, you can just simply set up the type of triggers that can be done on a digital channel or on the analog channels. So you can choose a combination on which you wanted to trigger. Along with that, you also have the multiple measurement which can also be selected on the specific channel respectively. Coming back to the signal that we have connected, as you can see from the channel number 5 and the channel number 6, which are the digital channel and the inductor current, we could easily identify when the channel gate pulse is high, we could see the inductor current, this is charging, is on the rising edge, and when the gate pulse is low, we could see that this is on a discharging mode. A very correlation between these two channels is very important when we are trying to debug these type of signals. It also helps you to analyze analog and digital channels simultaneously and to make a correlation between them in your measurements. Thank you.
So Nitin has nicely demonstrated about the mixed signal oscilloscope and its functionality and features. So here I just want to emphasize that since this course deals with digitally controlled DC-DC converter, so you need dedicated channel to analyze the digital signal as well as dedicated channel to analyze the analog signal. So particularly if you can see here the inductor current waveform, which actually has to be processed through the analog channel because we need to maintain linearity. Okay, that's why you can see the triangular waveform of the inductor current. So here we cannot process through digital channel because otherwise it will convert into some on-off pulses. That means it will lose the information of the inductor current. On the other hand, here you can see there are two signals which are, that means if you raise the current waveform, the first one is the high side gate pulse, because we are talking about a synchronous buck converter where we have both high side MOSFET and low side MOSFET, and as you know that in practical converter we need to provide a dead time to avoid shoot through current. So first it will be break and make. That means if you go to this, initially before if we zoom this portion, that means when you want to turn on the switch, that means first you have to do you have to turn off the low side switch, then you need to provide some dead time, then you turn on the high side switch. That means first you have to break the switch, that means that your conducting path, and then you turn on the switch. But this dead time amount, it is in the order of few like a tenths of nanosecond, around 40 nanosecond, but you can increase that. If you decrease the dead time, what will happen? Because the switches has some finite slew rate, rise time and fall time. If you decrease the dead time, there can be a situation when both the high side and low side MOSFET can be on, and that can short the ground and it can have a huge inrush current. To avoid that, we need to provide dead time. But if the dead time is too large, then it will turn on actually the low side diode will be activated and it will again cause losses. So that means we have to be very careful about the selection of dead time. And another important part, why people prefer digital control, another thing that we need to go for adaptive dead time, because if you consider this particular waveform, you can see the turn on turn off of the switches. That means if you are talking about turning of the high side switch, when the switch you want to turn on the low side switch, then the current which was flowing to the high side switch, it has to come down to 0, but the amount of current which is coming from that magnitude to 0, it depends on the load current. That means if the converter running at the nominal load, maybe to 20 ampere for example, then you will have the maximum inductor current and it will take longer time to reach from that full current to the 0 current. But if the load current decreases, then whenever the high side switch is on, the amount of current is low, so it can quickly come down to 0 during the turn of time. So if you provide a fixed dead time, which is a conservative choice, then it may so happen under the light load condition or maybe low current condition, you are unnecessarily turning on the diode and it can get into more lossy condition. That's why you may have to adaptively vary the dead time. That means as the load current increases, you have to increase the dead time. As load current decreases, you have to decrease the dead time. In this way, you can minimize the losses due to the diode reverse recovery. You can try to minimize that effect by means of adaptation, and this is why one of the reason that people go for digital control. So in this particular case study, that means we are running the buck converter. It has around 40 nanosecond dead time, and first your low side is turn off, then the high side is turn off. And if we look at this waveform, the gate signal looks a real gate signal. That means it can nicely capture the logic level as well as the rise and fall time of the gate signal. But same signal if you pass through the analog channel, because you can even see this signal, gate signal by analog channel. But the problem is this sharpness of the turn on and turn off of the gate signal require a very high bandwidth analog channel, and that is one of the limitation, because even if you go for 1 gigahertz oscilloscope, typically the roll off start even much earlier. So as a result, you will get a low pass filter effect. So your high frequency signals will be attenuated and it will not look like an actual square wave or the PWM wave. So you will lose the high frequency information at the turn on and turn off process. That's why you need a dedicated digital channel, and that is one of the purpose of using mixed signal oscilloscope, because you want to debug lot of, because in the FPGA what I have started demonstrating, and I will be demonstrating more video where we can check, because if you encounter some problem in the digital code, you want to debug it. So that means you have to pass some of the digital signal through your IO pin, and these digital signals are the logic signal which only takes 0 and 1. So you can take such multiple digital signals. Suppose you want to see here, we are using a mixed signal current mode control where the peak current reference is coming from the digital logic, and we are using a D to A converter. But we can also see what is the digital value of the peak current, and that can be analyzed by this digital channel, and you can figure out if any of this bit goes wrong. So you can easily debug the problem in your design and you can rectify. So that's why I would say the mixed signal oscilloscope is very useful, in fact necessary to debug and test and validate digitally controlled converter. And I think that was the purpose of today's lecture. Thank you very much.